We have seen AIMD. AIMD, in fact, has a small problem. It may take a time to converge that is not very, very short when the starting conditions are very different. This is showing here three sources. That one source starts with an initial value of 0, and the other two with values that are close. This is, for example, what happens to source number 3 in the previous simulation that started after the other two have already been using the network. We see that with additive increase, multiplicative decrease, so it will increase relatively until it hits the capacity, because the two previous sources were using the link entirely. A small increase here will already cause congestion, so it will hit a limit, will continue to increase, etc. It will converge because we use additive increase and multiplicative decrease that is guaranteed to converge. But it will take a large amount of time here, several hundreds of iterations. In TCP, every iteration is one round-trip time, so it's several hundreds of round-trip time until you get a share that is comparable to that of the others. Right? That's the problem of AIMD. So, in the way the internet was developed, we see a problem, we fix it. The fix causes another problem, we fix it, and we hope at the end we reach a fixed point where there is no problem left. We're not yet there, but close. So we added something which is an acceleration of convergence at the beginning. It's called slow start, unfortunately. It should be a fast start. With slow start, the idea is the following one. When a source starts, it will start with a small value. It will not start with a large value and then let AIMD take care of it. That would have been an alternative. This is why it's called slow start. The alternative to slow start would say you're a TCP connection. At which value do you start? Well, you take the maximum possible congestion window. So if you let the largest possible window, that would be a fast start. So in TCP, we don't do that. We start with a slow window, but we don't get to the equilibrium by using AIMD. Instead, we use very, very fast increase, but we complement that with what is called a target window or a slow start threshold. So slow start is in fact multiplicative increase as long as we don't receive negative feedback. So this is showing the rate obtained by a source in slow start. So we see it increases until it hits a limit here. When it hits the limit, the rate is divided, when it hits the limit, it is not the rate that is divided by 2, but there is another variable, which is the target rate. So the target rate is the large rate that we would have if we would start with a fast start. So the maximum rate that this source could have, it's usually a static value. With TCP, it corresponds to a fixed maximum window size. And then whenever we hit a limit, we look what was the rate that was achieved when we reached this limit. And then we set the target rate to half of the value which we had at that time. So we see the value here was 5 dot something. So when we have that, we get 2 dot something, which is the new limit. And then when that happens, we start again a new slow start from minimum value or close to 0 value, and we increase exponentially until we reach the target rate here. Of course, if we don't reach the target rate and there is another loss, then we will reduce again. So the idea is we sort of assume that there is a fair rate that you should reach, and this one we apply additive increase, multiplicative decrease to it, sort of, or at least the multiplicative decrease, by saying whenever we hit a limit, we halve this one by 2. But we will go very fast towards that limit. That's the idea of this algorithm. The algorithm concretely has a number of parameters that are the decrease factor, for example, 0.5, that's the AIMD decrease factor. Then it has the multiplicative increase factor, which in the internet is 2 here. And then initially we set the rate to a very small minimum value and the target rate to a very large value. And then we look at what happens. We receive feedback, positive or absence of feedback, Positive feedback means no loss, and negative feedback means we've experienced some congestion. Sorry. When we receive positive feedback, we increase the rate by this factor, which means we're doing an exponential increase. If, while doing that, we have reached the target rate, then that's the end of slow start. We consider that we are out of the transient phase and we exit the loop. If we receive negative feedback, then we restart the rate to 0, and we apply the multiplicative decrease to the target rate. So we multiply by U1. Of course, we always take max or mean values to avoid having arbitrarily small minimal values here. Here is what we achieve when we have the same simulation as before. So this is the rate that is in fact achieved by the last source, the red one. When it uses slow start, we see that if you compare to the previous simulation, we see that without slow start, we needed a large number of additive increase, multiplicative decrease iterations to obtain a rate comparable to the other sources. With slow start, we see that we very quickly increase and get in the same region as the other sources. And once we are in the same region as the other sources, we exit slow start, and then we run additive increase, multiplicative decrease. Here I'm mapping, this is a time diagram. On the x-axis is time, on the y-axis is the rate achieved by each of the three sources. We see that it converges very fast compared to without slow start. Here I'm showing an XX diagram, the source 1 rate versus the source 3 rate. We see that the source 1 rate is, the source 3 rate, is increasing very quickly. In fact, it's overshooting because this exponential increase is so fast that you can overshoot. But as soon as you overshoot, you start oscillating, and then you get close to the diagonal, which is the intended behavior, compared to without slow start, which was what I was showing before here. Voila, that's the theoretical underpinnings of what is done in the internet. The rest is software development that we will discuss in a few more minutes. Congestion control in the internet, which is necessary. Well, the first achievement was to recognize that there is a problem. Once this is recognized, then we need a control mechanism, and the control algorithm in the internet is very simple. It's based on additive increase, multiplicative decrease of the rate of the sources, and slow start at the beginning of a connection here. Of course, there are zillions of other refinements that we will now discuss. So now we go away from the world of mathematics and toy examples and simple simulation to what is really done in the internet. And because this is in software systems, it's always a bit more complicated. I thought it's easier to understand what happens in TCP if we do it in this way, if we first give the foundations. Because as you will see, there are many variants of TCP, which is typical of software system. TCP is done by software, so large companies, Google, Amazon, Microsoft, Apple, they all want their own TCP, and they all change something to TCP, and this is going on, and is probably not going to stop. Congestion control in the internet is in TCP. This is not an obvious thing a priori. TCP was not at all designed with congestion control in mind. Originally, TCP was to provide reliability to an application, relieve the programmer from having to count whether packets are missing and repeat them. It's also doing flow control, avoid that the destination is flooded by sources that it cannot, by a rate that it cannot handle, and that was it. Then came the congestion collapse in the 80s of the internet, and then very quickly people had to fix it and say, oops, we have a problem, we didn't think about it, we should quickly fix it. And then an obvious place to fix it was to do end-to-end control. Another thing could have been to change the routers fundamentally and do things like was done at that time. There were things called frame relay or X25, which were called virtual circuits, where each individual flow is visible by the routers, and the routers can pace the flows, can dictate how much rate is given. This is using explicit or implicit rate, but that would have been a fundamental change to the TCP/IP design. So more evolutionary solution is to add into TCP something that is end-to-end. Something end-to-end, therefore, put it into the transport layer. Now, why only in TCP and not in TCP and UDP? Well, because the belief at that time was that you use UDP when you do things like a short request, for example, a DNS request to a DNS server. Everything else is expected to be TCP. That was the thinking at that time. And we'll see that things are different now, and we'll see how we'll take care of that in a second. Why also we used the thing in TCP, and why did we do AIMD, additive increase, multiplicative decrease? Well, because at that time there was already a network that did not have any form of congestion collapse and was using an architecture very similar to TCP/IP. It was the DECnet, the network of the company Digital. So that one was using exactly additive increase, multiplicative decrease. Therefore, the solution existed. It was easy to apply it to the internet. What is the negative feedback? In DECnet, it's a special bit in packet headers. We will see that the internet many, many years later thought it's also a good idea to have it, and it's called ECN, Explicit Congestion Notification. But at that time, this was not done. So the decision was the symptom of congestion is loss of a packet. Very typical of the way in computer science we reason about things. We see what is already existing, and if we can use something that exists, we do, instead of inventing something else. Right? So because we know writing code is very, very, very complicated and takes always 10 times more time than we think it would do. So if we can do the thing in a very simple way, we do it. But as we will see, it has also some drawbacks that we are trying to mitigate with ECN. Another issue is, of course, now, at that time, the only large amounts of traffic were TCP, so ignoring UDP was okay. This is no longer true. In fact, a large volume of traffic today is UDP because Chrome and all the Google applications tend to use QUIC, which is an alternative to TCP. QUIC is an application layer framework, which is very similar to a transport protocol, but it's using UDP. We'll talk about QUIC in a few weeks. So if you do something like QUIC, you have to do congestion control. For QUIC, the solution is easy because QUIC was invented very, very recently. They simply imitated everything that TCP is doing. So QUIC is also counting packets, putting packet numbers, so it's very similar to what TCP is doing. It adds security and avoids head-of-the-line blocking. It has a number of complexifications and improvements. But essentially what QUIC does is it takes exactly the code that exists in TCP congestion control and implements it. And that's a general thing. If you do a UDP source, and if you expect that source to send more than one packet once in a while, you have to do congestion control in the UDP source. The word for that is, we say that UDP sources should be TCP friendly. Instead of saying they do congestion control, we say they should imitate TCP, not in the sense of all the bells and whistles of TCP about silly window syndrome avoidance and other details of TCP, but in the sense of congestion control. That's what TCP friendliness means. Now, TCP, we have already discussed, has a number of small algorithms, number of variants. But the most striking differences in different versions of TCP is really the congestion control algorithm that's implemented. The reference congestion control method, which is the one that is still influencing all designs that are done today, is the one of the version called TCP Reno. Reno is the name of an American city, I believe, in somewhere in the west. We will see new versions that are cubic and data center TCP, because those two versions are very widespread today. TCP Reno and variants are the basis for main software providers' versions of TCP. TCP cubic is the one that we find in Linux servers in particular, therefore in a large number of servers in the world. And data center TCP is also very widespread in specific environments. So we'll talk about all this. Then every 2 years, there's a new revolutionary version of TCP. We'll talk of one example of it and say what has to be believed about it. All these versions are just changing a few details. They're not radically changing the thinking that we have seen in the first part. They do AIMD or very small variants of it. And they all use what is shown here. So TCP implements an approximation of additive increase, multiplicative decrease, AIMD, and also slow start. But how does it adjust the rate? Well, it uses this formula that we have seen already that says that if there is no loss in a network, and if you have a window flow control protocol, like TCP, that imposes a window W, the rate that you can achieve is W divided by RTT. That's the rate that the source has. So if you want to manipulate the rate, the RTT is hard to manipulate. It's the result of what happens in the network and the servers, but you can manipulate the window. So what TCP does, in addition to all the things we have seen of TCP, it maintains another variable, which is called the congestion window, CWND. And the actual window size that may be used by the sliding window protocol of TCP is the minimum of two things. The minimum of what we had seen before, the offered window, that's the value that is in the reverse path in the acknowledgements that you receive from the other end. There is a field called window, and that is for flow control. That's for protecting the receiver. In addition, there is another variable maintained locally by the source, CWND, and it's the minimum of the two. So CWND controls the window size. It forces the window size to be not larger than that. Now, a TCP sender may be limited by congestion window, in which case it means it's the network that limits the rate at which it is sending, or it may be limited by the offered window, in which case it means that's the receiving application that is limiting the rate. In this analysis here, we will focus on the case where it is the network that limits the rate at which the source is sending. The negative feedback, as I said, is the loss, and the positive feedback is when we receive acknowledgements. Here. We will see how additive increase and multiplicative decrease are done. Multiplicative decrease corresponds in theory to a factor of 0.5, so when we detect a loss, we divide by 2 the window size. The additive increase, which is a linear term, added is equal to 1 MSS, 1 maximum segment size, per round trip time. This is how much we increase when there is no loss here. The slow start is with a factor of 2. We double by 2 per round trip for every round trip time where there is no loss that is observed here. Second, slow start is executed at the beginning when we start a connection, but also in other circumstances when loss is detected by timeout. Why do we do this? Well, the belief or the reasoning, it's an approximate reasoning. We don't know what really happens in the network, but the belief is the following. At the beginning, we should do slow start because we have no clue what is the fair share that we're trying to reach. So we start from very little, from 0, for 1 packet per round trip time. And then we increase very fast until we hit a congestion, and then we will do AIMD. When a loss is detected by timeout, the belief is that this is not usual. Normally, if you have an application that sends a long stream of data, most losses should be detected by fast retransmit or other heuristics. We've seen there's a number of them, but those are heuristics that are trying to see what happens when packets are lost in isolated way. And most of the time, this is what happens, but not always. And the belief is that if a loss is detected by timeout, it is because there has been a serious change in the network. And a serious change in the network means, well, we should restart things. We should be on the safe side. Being on the safe side means doing slow start. Of course, this is not always true. We have seen cases where we can simply have loss detected by timeout, not because there is a serious change in the network, but, or in the conditions in general, but by bad luck. For example, your number of duplicate ACKs should be 3, and you've sent only 2 packets, so you will never receive a third duplicate ACK, so you will need to wait for a long time until the loss is declared. And then if that happens, well, with this heuristic, we will consider that we have to do slow start. But that's the belief. So all versions of TCP do that. When a loss is detected by timeout, they get into slow start. In all other cases, they do something milder. They do additive increase, multiplicative decrease, as we will see next. Part of the difficulty in understanding how TCP works, the congestion control of TCP works, is realizing 2 things. First, TCP is based on the model we have seen in the first part of this lecture, on the additive increase, multiplicative decrease, which is based on reasoning on toy models with rates and feedback that indicates congestion or not. But, and that's the second part, in reality, what TCP is doing, it is embedded this into a system that has no notion of rate, but instead is manipulating a window and is receiving acknowledgements. So there is a mismatch between the theoretical basis on which the analysis was done, which has to be simple to be tractable, and the reality, which is windows and packets and acknowledgements. So here is one of the examples how things are a bit different. How do we do so the additive increase? Additive increase says every so-and-so in the model, the word every round trip time, for example, if there is no negative feedback received, increase the rate by some constant amount. One way to do that, and some TCP implementations do it this way. So what they do, they wait until the current value of the congestion window is completely acknowledged. And when this is happening, they increment the congestion window by 1 packet. This will not do exactly what I said before, because the time it takes to to acknowledge a complete congestion window is more than the round trip time. It is the round trip time plus the time to send all the packets in the window. If the window is large, it may be much, much more than the round trip time. That's one of the implementation that is possible. An even simpler implementation, so this requires counting things with windows. Do I have a full window acknowledged, etc. A simpler implementation that is done by some versions of TCP, that's the historical implementation, is the following, is this one. Whenever I receive an acknowledgement, I increase the congestion window by the square of the maximum packet size divided by the congestion window. It seems a bit mysterious, but if you imagine, well, we have to do a congestion window in bytes, so you need formulas like this. But to understand this formula, imagine that all packets are of the same size, equal to MSS. And you count the congestion window in MSS. That means you should divide congestion window by MSS, and the increase should also divide it by MSS. Then if you count in packets, this means you increase the congestion window by 1 over the congestion window. So that means also that if you do that, if the congestion window is n, if you do that n times, you have increased by 1 over n times, so at the end you have increased by 1. Except if I'm doing that, I'm a poor mathematician, because if I increase by 1 over n plus 1 over n plus 1, etc., the sum of that will not give n times 1 over n, but not far. This is illustrated here. Assume the congestion window is 1 packet, 1 MSS. So if it's 1200 bytes, the TCP code will write 1200 bytes, but here I count in packets. When I receive an acknowledgement, I increase that by 1 over 1, that gives 2. So the window is increased by 2, which is what we wanted. In 1 round trip time, we increase by 1. Then when I receive the acknowledgement of the first packet, I increase by 1 over 2. That gives me 2.5. When I receive the second acknowledgement, I increase by 1 over 2.5. That gives me 2.9, which is not very far from 3, and etc. If the window is 3, after receiving that, I will have 383. So the very first implementations of TCP did this, which has the virtue of being very simple, and is sub-approximation of 1 increase per window. So it's a bit less than additive increase in the sense if the window is large, if the rate is large, we increase by a bit less than 1 MSS per round trip time because it's 1 MSS per congestion window. And there is also this fact that we don't increase by 1 over 0.5 at every one here, but 1.05, 1 over 2 plus 1 over 2.5, etc., which is a bit less than linear increase here. So this is how additive increase is implemented. If you look at your favorite TCP code, you will find something which is either this or that. The multiplicative decrease is very simple. When the multiplicative decrease occurs when we detect a loss, in that case, we multiply the window by 0.5. We will see which window is in fact multiplied by 0.5. When we do slow start, we do multiplicative increase. So we should increase the window by 2 every round trip time or periodically. So here a similar trick is done. The congestion in window increase is, in fact, for every acknowledgement received, you add 1 MSS to the congestion window, which is saying that if we would count in packets, we increase by 1 for every acknowledgement received. So you see on this simulation that when the window is 1, we receive an acknowledgement, the window becomes 2. When it's 2 and we receive all the acknowledgements for this window of 2, then we increase by 1 plus 1, so we double the window, etc. So in every time it takes to transmit a full window, we double the window size, which is not exactly also multiplicative increase because the time it takes is a bit small, is a bit larger, but is close to that. This is how TCP approximates the multiplicative increase. So if we observe the value of the congestion window variable kept by a TCP connection, we will see typically something like this. At the beginning, we start from a value which is the smallest possible value, 1 or 2 MSS. Then it increases exponentially using multiplicative increase. The slow start threshold is initially a very large value. When you have a loss here, we restart slow start, but with a slow start threshold, which is half the value we had obtained at the loss. So we will probably very quickly exit it. And then we increase the window for every acknowledgement received, doing this approximation of additive increase until there is a loss. And if the loss is detected by timeout, as is illustrated on this figure, we will go into slow start again. But in that case, the slow start threshold, so the target window, is equal to half of the window just before the loss. This is how we implement the multiplicative decrease. So it will oscillate in this way. It's not exactly like the oscillations that I had shown on the previous simulation. We see that when there is a loss here, the window size is really going to the minimum value and exponentially fast increases back to half the value. This is what you will see in TCP whenever all losses are detected by timeout, which is not the typical case. In the most typical case, losses are detected by one of the heuristics such as fast retransmit. And when that happens, we need to fix a problem. The problem is illustrated on this animation here. Here I'm showing on the left, so time is going down. On the left is a TCP sender. And I'm showing the congestion window and the slow start threshold, which is the target window whenever we are in slow start. But we'll see that we continue to use it also in other phases here. And in red are the sequence number of the packets that are being sent here. I assume packet sent at time 2 is lost, and we receive acknowledgements. So we see that when we receive this acknowledgement here, we increase the congestion window by 1 over the congestion window, which gives a small increase here. Then the window size is 800 and so. So I can, since I have received an acknowledgement for byte 201, I can continue to send packets here. Right? Until at some point I receive 3 duplicates, so that happens at line 12. At line 12, here I'm assuming the number of duplicates that is configured in this version of TCP is 3. So when I received 4 times the same sequence number being acknowledged, which is 201 here, occurs at that time, I detect the loss. Right. Now, if I detect the loss, what should I do? Well, if I would do the straightforward application of multiplicative decrease, I should divide the window size by 2. So the window size, the congestion window size, which was 800, should be reduced to 400. Right? But what happens if we reduce the window size to 400? Well, the window size is 400. I've received acknowledgement to 200, so I can send only packets up to number 600, which is already too late. I have sent already the packet 700, and since I have already sent everything that was possible, and more even, I cannot send anymore. So if I apply the multiplicative decrease in this case, and that's a very frequent case, I'm effectively stopping the source. So I'm not doing multiplicative decrease, I'm doing set the rate to 0. And why is that happening? Well, this is because the formula that says that the rate that I'm controlling is equal to the window divided by tau, this is true only when there is no loss. If there are losses, then the window becomes blocking. Here, that's the case, where the window is blocked at 200, so I cannot send, in fact, I cannot continue sending packets. If the window, because the last ACK is, because a packet was lost. So a packet was lost means, due to the sliding window mechanism, I cannot continue sending more than everything acknowledged since this packet lost. If we did not have a window flow control, like we could imagine having, but we had good reasons for having it, for avoiding buffer overflow at the receiver, then I could continue sending 400 packets from the one I have already sent. But the sliding window principle says, no, you're not allowed to send 4 packets from now. You are allowed to send only 4 packets from packet number 2, from byte number 200. In that case, that means stopping the source. So there is a mismatch between the rate control and the window and controlling the window. In this specific case, controlling the window does not result in what we would have. So what do we do? Well, we could change the rules and drop the idea of having a sliding window. That was not done. Instead, a heuristic was done, which is the heuristic explained here. When you detect a loss by n duplicate acts, here 3, you continue increasing the congestion window to avoid the problem I said before, and you increase it exponentially fast, like if you were in slow start in some sense. But you remember the target window, which you continue to call the slow start threshold, even though there is no slow start here. You multiply the current size of the window by 0.5. And let's see on the animation what this gives here. Here we are in this mode here. For every acknowledgement, so when we get here, what we do is we divide this window by 2, and we recall it. That's now the value of the target window, which in TCP folklore is called slow start threshold. So that gives 407. Then we add 3 packets, 3 MSS to the current to this, and we consider that this is the congestion window. So this is more than that. That will allow us to continue sending some stuff. And for every acknowledgement that we receive, we continue increasing the congestion window. So that will allow us to resend the missing packet, continue sending 1 packet. And as we receive new acknowledgement, we see that the congestion window continues to increase. It increases exponentially, but remember here, that doesn't mean that the rate at which we send is exponentially growing, because we are blocked by the window and the fact that we have not received acknowledgement after number 201. And then, since we're allowed to resend, we resend, and then sooner or later, we will receive, this is occurring at time 19 here, we receive an acknowledgement that repairs the loss. Here, the retransmission that was sent here is acknowledged here. So at that time, now, we exit this special phase, which is called fast recovery. And we set the window size to the slow start threshold, the one we had kept in memory. Because now we are not blocked anymore. We have repaired the loss. So now, by giving a window of 400, we are effectively controlling the rate to what we would like it to be. Well, that's the kind of complications that occurs due to the window and packet nature of TCP. Small break and question here. When we finish this simulation and we are at time 20, what can the source do? How many new packets can it send? And the correct answer is C. This one here. We've seen that 4 is a frequent answer. But in this case here, the advertised window, the congestion window is 400. The advertised window is 1,000. So this one is larger. That means the congestion window that is limiting. And the last ACK receive is 900. So this packet that has been sent here has not yet been ACKed. Therefore, we start from here. So that means at this point, we start a pipeline with a window size of 4 packets. Since one has been sent already, we can send 3. That illustrates the thinking of this heuristic and the kind of heuristics you need to do to have TCP to work. When there is a loss, that's detected by fast retransmit. We do not have the window by 2, because if we would do that in many cases, we would stop the connection entirely. Instead, we do this heuristic, which is called fast recovery, which is trying to do the best in the average case to avoid this brutal stopping, but still, as we can see, limits the window by 2 once the packet has been repaired. Another question to your sagacity. And the majority says B. So if we have losses that are due to a wireless link and not to congestion, well, the TCP sources have no way to know that it's due to congestion. I mean, a loss is the absence of something. You don't know why something is absent. So there is no mechanism in the internet today to signal to a source that the loss is due to something else than congestion. Therefore, losses will reduce their rate. If it happens during slow start, it will reduce also the slow start threshold, etc. That's an unfortunate, so answer B, that's an unfortunate result, right? That's, in some sense, it's a bug of congestion control in the internet. We have lots of wireless links. The wireless links are a bit random. Even if you do all the stuff with MAC layer acknowledgements, you cannot guarantee that something will not be lost simply because of a wireless propagation error. If that happens, your sources will think there is congestion and will reduce its rate. That's one of the reasons for poor performance over wireless links. That's one of the reasons that dictates a lot of developments in the internet today. Things like content distribution network, things like trying to put the content very close to the base station, because if you're downloading data from California all along the way, and the packet is lost just on the last wireless link between you, you will do the same as if you think the server is congested in California, right? So you will reduce your rate and perhaps get bad performance. Right? So if the server is really congested and you have a wireless link that loses packets, then you will have much, much worse performance than others that are competing for the same server as you. Right. That's a reality. It's an unsolved problem of the internet. I hope some of you in the future will work on solving it and making the wireless internet better. Now we have seen that TCP is, or this version of TCP, TCP Reno, is approximating AIMD. So we could ask the question, what does it do in terms of fairness? What kind of Pareto efficient allocation does it provide in the network? And the answer is, well, close to it. So the math was done with simplifying assumptions. We find this formula. Assume you have a network with a large number of sources that use TCP to control their rate. So we ignore the other sources. And also assume the sources are doing large transfers so that the system, the rates can converge to their average values. Then everything is as if we would be optimizing this utility function. So it is distributing rates according to a utility fairness. Now this function is this one, arctangent of this. Now, why arctangent? Why log in the previous case? Well, this is when you do the maths of the ordinary differential equation that you obtain, you need to integrate something somewhere. In that case, there was a 1 over 1 plus x squared. In the previous case, there was a 1 over 1 plus x. You obtain this. As a first approximation, it's not very important because if I plot, once I rescale the function to have the same value of 1 when the rate is 10, and I plot in blue the function with the log that I had before with AIMD, or in red stars the function that I have here, I obtain quasi the same. So we could say, well, no big deal, why worry? But there is a difference. If we look at the formula here, in order to obtain the same function, I had to set the RTT to some value. What we see here is that the utility function depends on the RTT. Here the RTT is tau. So the RTT of this source plays a role in the utility function. Right. Now we see that it's 1 over tau, and here it's tau. So it's not very clear from this formula how it depends on RTT, but it's not difficult. We can easily plot here. Here I'm plotting the value of the utility for a given x as a function of tau. And we see that this decreases and this increases, but arctangent is a very slowly increasing function. So these terms dominate. So this is a decreasing function of the round trip time. The utility that TCP allocates to a source is less if this source has a large RTT, and is more if this source has a high RTT. So approximately within the limits of this analysis, it means that in the internet we can imagine that the rates are allocated to the sources that are competing as if somebody was doing a social planning exercise, maximizing their utilities. What does it imply? What does the fact that the utility is less if you have a large RTT and vice versa with small RTT, what will it imply? What will be the consequence? Well, if I am the social optimizer, say I am in a socialist country, or I need to allocate the rate to all the sources, then I have to do compromises, because some I will, as I'm hitting some limits, I can increase your rate, but I will need to decrease the rate of someone else. Now, if I want to increase someone and decrease someone, who will I decrease more? Well, I will decrease more the guy that has a smaller utility, because I'm maximizing the sum of the utility. If your utility is very small, the utility is like if you pay to me in fraction of utility, you pay to me 1 franc per unit of rate, and you pay to me 10 francs per unit of rate. Then I will give more rate to you because I will get more revenue. So what we expect is that in the internet, connections that have a very long RTT are penalized. They get less than their fair share because of their large RTT. Voilà, this important topic we will continue to discuss next week.